Good morning, ladies and gentlemen. We're going to talk about increasing, decreasing functions and concavity of functions today. These are sections 3.3 and 3.4. Our objectives are that we're going to use our first and second derivative tests to determine the intervals where our functions are increasing, decreasing, or have concavity. All right, so I just want to go back. We're going to do 3.3 first, obviously. That's kind of a does statement. And talk about a function just to remember your brains. So let's say I have this cool little function, okay, that looks kind of like that. If I want to look at what's happening, notice that the y values are decreasing as the x values move to the right. And so we would say that this portion of the graph is the decreasing, okay? And then over here, the y values are increasing as we move along the x-axis. So this is the increasing portion of the graph, and I'll write decreasing over there. And then if you'll notice right here, the y values are staying the same as I move along the x-axis. So this is a constant portion of the graph. So then if we start talking about this from a calculus standpoint, the slope of the tangent line is negative. The slope of the tangent line is 0, and the slope of the tangent line is positive, right? So we can use our derivatives to help us determine the intervals of decreasing constant and increasing on our graph. Alrighty. Remember, this is information from last year and from pre-calc. If I want to talk about an interval where a function is increasing, remember that we always use open brackets, okay, because we don't know exactly the point at where that changes, so it would be difficult to get close enough to find an exact point, so we leave those brackets open. Same thing if I'm talking about where a function is decreasing or where a function is constant, then I'm always going to use my open brackets where those pieces of information are not included. There's two primary ways to manage, so I'm going to write we're going to manage the first derivative test. And I'm going to actually use a combination of the two methods. So the first method that people like to use is they would use a sign chart. And then the second method is to use a tabular method. And then I actually like to use one that is a combination. I tend more toward the tabular method, but then I also need the sign chart to help us with our graphs, okay? All right. And the first derivative test, since we probably should go back and restate what that is helping me to determine, so it determines intervals of increasing, decreasing, or constant. So let's walk back through that basic process for using the first derivative test to determine the intervals where a function is increasing, decreasing, or constant. So the first step, so I'm going to do steps of our first derivative test. So the first one, obviously, is to take the derivative. So I'm going to take the derivative of the function, and then I'm going to set my derivative equal to 0. So I'm going to set my derivative equal to 0, and I'm going to solve for x. And if you'll remember, these are called the critical values. Okay? And we're going to use those to help us determine the intervals of where things are increasing, decreasing, or constant. Once we know what our critical values are, I would say that you should sketch it because I think it helps to not make silly mistakes. And we're going to choose the intervals to critique. And I'll walk us through an example because I think it will help a ton. And then once we critique, we're going to look at the signs. Okay, so we're looking for increasing or decreasing of the derivative evaluated in these intervals. Okay, and then once we have looked at the signs, then we can determine the intervals, which was the whole point of the problem, of increasing, decreasing, or constant. Okay? We can, oops, I'm sorry, you can't see that. We can also use our graph, our first derivative test. So this is kind of an aside. This is a nice thing to determine our extrema. So we can use our first derivative test. I'm getting lazy with writing out my words. To determine our extrema, or the lack thereof. So we'll talk about that as we kind of walk through our example. All right, so those are kind of the processes that we're going to use, and then I'm going to do an example, or we're going to do an example to go back and remember this process. All righty, so as we said, I tend to use a mix of the two methods. So we're going to find, in our first example, sorry, I forgot the example part, find the extrema of f of x is equal to x squared minus 4 to the 2/3. And we're going to do this without a calculator so we can go back and remember how useful this process is, and then in the end you can put it in your calculator and look at it. All right, and then this would be my plug for Desmos. If you don't have Desmos on your phone, get it on your phone. It's a free app, and it's glorious for graphing. So the first thing that I'm going to do is I'm going to take the derivative of my function, and it is the chain rule, so this is going to be 2/3 times x squared minus 4, and then 2/3 minus 3/3 is the negative 1/3 times the derivative of the inside, which is 2x. And I'm going to clean that up. So I'm going to say that my derivative is going to be 4x over 3, and then I'm going to stick my little cube root guy down here, x squared minus 4. Okay, so there is my derivative. Alrighty, so I'm going to set this equal to 0, and I'm going to find my critical numbers. But before I do that, I also want to consider not only where the function is 0, so I can solve for 0, but I also want to consider what makes the denominator be undefined, because the world would explode. So if I look at that, if x is a plus or minus 2, and I square it, then I'm going to get the cube root of 0, which is not a big deal, but it is when it's in the denominator. So our points of discontinuity potentially could become some of our critical numbers. Sorry, brain and mouth aren't working at the same speed. But then if I wanted to solve for x, I would cross multiply, and I'm going to get that 4x is equal to 0, so x is 0. So these are going to be my critical numbers. Alrighty? So what I'm going to do next is I'm going to stick those little guys on a number line, because I'm a visual human and I like to see what I'm doing. Here's my 0 and here's my 2. And then I'm going to set up my tabular method. So I'm going to critique this interval right here. So my first interval is going to be a negative infinity to a negative 2. Remember, they're not included. My second interval is going to be a negative 2 to 0. My third interval is going to be 0 to 2. And then my fourth interval is going to be 2 to positive infinity. And if you'll remember, what we like to do is choose test values in those particular intervals. And I'm going to write them up here. So I'm going to pick a negative 10, a negative 1, a 1, and 10. Okay, so those are just going to be my test values. So then I'm going to do my derivative evaluated at a negative 10. Well, if I do that, I'm going to get, and I'm looking at my numerator, so I'm going to write this over here so you can see it. So I have 3 times the cube root of x squared minus 4. If I put a negative 10 into the numerator, I get a negative in the numerator. And if I put a negative 10 down here, this is a positive 100 minus 4. This is positive. The net effect is negative, and that's what I'm concerned about. Okay? Alrighty? Then I'm going to evaluate and it's kind of written a little bit kludgy, but I'm going to evaluate in this particular interval, I'm going to evaluate my -1. Okay, so if I substitute that value in, I get a -1 in the negative in the numerator, and then if I put 1 minus 4, the cube root of a negative is negative, so I'm going to have a negative in the denominator, so the net effect is positive. Okay, and I should have put that little f of -10 in there, but life goes on. All right, in this interval, I chose to test a 1, okay, and I really don't care what the value is. All I'm looking at is the sign. In the numerator, it's positive. In the denominator, 1 squared is 1 minus the cube of a negative is negative, so I have a negative. Net effect is negative, okay? And then I'm going to do, sorry, I'm evaluating f primes in here, f prime of 10. And if I put a 10 in the numerator, I get positive. And if I put a 10 in the denominator, I get positive. Net effect is positive. So now what I want to do is kind of critique my graph. So remember, this is my derivative. This is f prime of x. And if the slope is negative, that means that the tangent line has a negative slope. Sorry, bad grammar. In this particular section, the derivative is positive, so it means I have a positive slope. In this one, it's negative, and then in this one, it's positive. So I have a couple of different things going on in my little intervals. Right here, I have decreasing to increasing, so this is going to be a minimum at x is equal to a -2. Up here, I have a positive and a negative slope, so this creates a maximum at x is equal to 0. And then down here, I go negative to positive. This is another minimum, and it's going to be at x is equal to 2. So that allows me to have some criteria about my function. Alrighty? So I know if I was to report extrema, I've actually solved the problem. So I would say, here's my extrema. I do want to keep going a little bit just to talk about sketching curves. All right, so for my extrema, I can say that I have a minimum at x is equal to plus or minus 2, and I have a maximum at x is equal to 0. So then if I wanted to, I could critique and find out if they were relative or global or absolute. But at this point, they just ask us to find extrema, and so we could stop here. If I wanted to find the y values of these points, I could evaluate f of plus or minus 2, and I could evaluate the original function at 0, and then I could find the coordinates for my extrema. But what I want to do next is talk about the graph a little bit and talk about what we have found. Alrighty, so in our table of values that we critiqued, we found that the slope of the tangent is negative, which means it's decreasing, right? And then we found that the slope of the tangent is positive, the slope is negative, and the slope is positive, okay? So then if I evaluate these critical points, at f of a positive 2, I would get 0, and at f of 0, I would get some number, which is going to be a -4 to the 2/3, so whatever that happens to be. So I'm going to write a number. And then if I have f of a -2, I also get 0. So I know that for my graph, that these are going to be my x-intercepts. Well, if I look at the information from the tangent, it appears that I decrease, hit the axis, and bounce off. So if I wanted to think about sketching my graph, okay, so at a -2, I have a negative tangent, and then I'm going to bounce off and become positive, okay? I kind of have a hard time keeping it in your window today, all right? And then when I get over here to 2, I have on the left-hand side of 2, I know that the slope is decreasing, and then on the right-hand side of 2, it's increasing. So I know that my graph is going to look something like this and this, and I know that this is a maximum because we determined it, and I can actually find it. So I can actually kind of get a decent sketch of my curve right there. Okay? If I did f prime of 0, which is interesting, we would potentially get that I could have I'm going to have, a 0 in the numerator, which means that I'm going to have a horizontal slope right here, which is another tool that I could have used to help me know that I have a horizontal tangent at x is equal to 0. So there's lots of things that we can learn from our extrema. All right, the next thing that we're going to talk about is the extreme value theorem. Okay, and yes, we are building up to curve sketching, but we'll get there shortly. This is an existence theorem, and basically his claim to fame says that an extrema is going to exist in an interval, and we'll call it a closed interval, where we have a derivative equal to 0. So if the derivative is equal to 0 in a given interval, then I know at some point in that interval I'm going to have an extrema. It doesn't tell me what kind, it just tells me that it exists. All right, if you're asked to verify extrema in an interval, okay, so if you are asked the task of verifying an extrema, the first thing that you're going to do is find the derivative, and then you're going to find your critical values, which means I set my derivative equal to 0, right? So that would be set your derivative equal to 0, and we're going to solve for x, or whatever variable happens to be there, okay? And then I want to evaluate the function at, and let's say I found, bad grammar. Here's the endpoint. I need to evaluate the endpoint because we always tend to forget that. And then I'm going to evaluate the other endpoint. And then I'm going to evaluate my critical values. Okay? And then I can know numerically, and this will be my verification of my extrema. And it could be a verification of minimums or maximums, but I will verify my extrema based on the values that I get when I evaluate the function at the endpoints and at the critical values. And these are the two that we tend to forget the most. We forget to evaluate our endpoints. All right, so the next thing I want to do is clarify and make sure we understand the difference in a couple of theorems that we've gotten. So I want to clarify 3 theorems because it's important that you understand how to use the 3 of them should it pop up in a given situation. So the first one is Rolle's theorem. And basically this one says if the function is continuous and differentiable, that's a D, and differentiable on a open interval a to b, then there's at least one horizontal tangent if f prime at some value is equal to 0. So basically what Rolle's theorem says, it's an existence theorem, and it says that if the derivative is equal to 0 in a given interval, then I know that I have at least one horizontal tangent. Okay? The next one that we got, hugely important, we see this one all the time, is the mean value theorem. And this is actually a really cool theorem because this one states that the secant, the slope of the secant line, is going to closely approximate the slope of the tangent line at a given point, right? So the mean value theorem basically gives us a way of calculating the slope of a tangent line even if I don't know an equation for the tangent line. So it's very, very useful. We often see it called the average rate of change, and that would say that the derivative at a point, even if I can't calculate the specific derivative, is just the slope in between the end points of the interval. So if I have an interval a to b, the average rate of change in that interval is just the slope of the secant line in that particular um, interval. Get both of my fingers in there. Alrighty? Very, very nice theorem. The third theorem that I want to talk about is the extreme value theorem. And again, it is an existence theorem. Okay, so we've had a couple of different existence theorems, but this one says if there is a horizontal tangent, and I know that because I would get f prime at a constant is equal to 0, right? The slope of the tangent line is 0, so I would have a horizontal tangent in an interval from a to b, then I have, or then there is, an extrema in the interval. So the extreme value theorem says if I have a horizontal tangent in an interval, then I know that that is going to be my extrema. Alrighty, so the next thing we want to do, we're actually into 3-4 now, is talk about concavity. And it's going to be concavity and the second derivative test. So the first derivative test showed us where the function is increasing, decreasing, or constant. The second derivative test shows us where the original function, so second derivative test, is going to show where the function has intervals of concavity and if my second derivative is positive, then I know that f is concave up, okay? And if the second derivative is negative, then I know that the function is concave down. There is another use for the second derivative test, and we'll talk about it at the end. Alrighty, so remember that concave up means I look like a bowl. Concave down means everything's going to spill out. And then the other vocabulary word that we have is an inflection point. And this is where a change in concavity occurs, right? So wherever the function, the original function, changes concavity, that is called an inflection point. A couple of other things to remember, just because this shows up every once in a while. If I am solving for x for my critical values, so in a critical value, and if I got an imaginary number, so let's say x critical was equal to some type of imaginary number, remember those do not show up on our real number plane because I like to throw tricky things in every once in a while. On a real number plane, so therefore it's not a critical value. And sometimes when we're doing our second derivative test, if I can't find a critical value, I may have to resort to my vertical asymptotes, okay? So if I'm trying to solve for the critical values and I got an imaginary number, I would have to switch and resort to using my vertical asymptotes. Alrighty, so here are our steps for determining intervals of concavity, very similar to the first derivative test. And in theory, you would have a function. So our first step is we're going to be given a function. Then I'm going to take the first derivative, and then I'm going to take the second derivative. Okay? Once I take my second derivative, I'm going to find the critical values from the second derivative, which means that I set my second derivative equal to 0 and I solve for x. Okay? And then I can critique the intervals. And remember, I am looking for positive and negative information. I'm looking for the signs to help me determine my intervals of concavity. All right, so let's do an example. What color pen do I want to bring in now? Where we look at finding intervals of concavity. So the example is going to say determine the points of inflection and then discuss the concavity of the graph. And we're almost done. So I have this example, and then I want to go back and review curve sketching just a little bit, and I keep yanking on the cord in my computer. Poor baby. All right, so let's say in this particular example, you're going to be given the function f of x is equal to x to the fourth minus 4x cubed. And I'm going to manage my information just like I did in the last problem, where I'm going to kind of do a combination of the tabular method and a sign chart. My first derivative is going to be 4x cubed minus 12x squared. My second derivative is going to be 12x squared minus 12x, oops, bad math, 24x. I'm going to set my second derivative equal to 0, and then I'm going to factor. I'm going to factor out a 12x, and I'm going to get x minus 2 is equal to 0. So I know that my critical values are going to be x is equal to 0 and 2. And then it just helps my poor little pea brain to put it on a number line so I can look at it. So I'm going to have my interval 0 and 2. So when I start critiquing my function, I'm going to have the interval of a negative infinity to 0, and then I'm going to have 0 to 2, and then I'm going to have 2 to positive infinity. Okay, draw my little table in here. And I'm going to evaluate the second derivative. I'm going to do a negative 10, a 1, and a positive 10. There's nothing special about those numbers. They're just nice, polite numbers. When I substitute them into my second derivative, I'm going to do it in factored form because it makes my life easier. So if I evaluate the second derivative at a negative 10, the first value is negative. The second value is negative. So then that means the net effect is positive. Okay. If I evaluate the second derivative at 1, the first number is positive. 1 minus 2 is negative. So the second one is negative. Okay. And then if I evaluate f double prime at 10, the first number is positive. The second number is positive. And so that means that the net effect is positive. Okay. So if my second derivative is positive in an interval, that means that it's concave up. If my second derivative is negative in an interval, that means it's concave down. And then if I have positive, then it may be concave up. The cool thing is I can get a pretty good idea of what the graph is going to look like just based on the concavity from down here. So then the problem said determine the points of inflection. Well, the points of inflection are going to happen where there is a change in concavity. I know the x coordinates, but I have to find the y coordinates, so I'm going to do f of 0. Notice that this is the original function. So I'm going to get 0 to the fourth minus 4 times 0 to the third, which is 0. So I'm going to have an inflection point at 0, 0, and I'm going to do IP just so we know what we're doing. And then I'm going to evaluate the original function at 2, so 2 to the fourth minus 4 times 2 to the third. When I do that math, I get a negative 16. So my second inflection point is going to be 2, negative 16. So then I would report my answers. So I would say that I have inflection points at 0, 0 and 2, negative 16. And then for my concavity, if I discuss the concavity, I would say that the function is concave up in the intervals at the t, negative infinity to 0, and 2 to positive infinity. The function is concave down in the interval from 0 to 2. So I think this kind of mix of tabular and graphic is really nice because I can see a lot of information right there. Alrighty, the last thing that I want to talk about is just to kind of go back and do a little bit of a review on curve sketching and just to talk us through and start that conversation. Okay, so we're going to start with, here's our first graph, and I guess I made it kind of big. I'm going to start over because I need it to fit, all three to fit on a page. So I'm going to start over, my bad. So make him a little smaller. So here's my curve sketching. Here's the first one. Oops, so much better. So I'm going to have a graph of my function that's going to look like this. Okay? So this is going to be f of x. And things that we notice about this, at this point, my tangent has a positive slope. At this point, I have a slope of the tangent is 0. At this point, the slope of the tangent is 0. The slope of the tangent is decreasing, and then over here, the slope of the tangent would start increasing. In this particular area, this is going to be concave down, right? And then this one is concave up. Okay, so we're just looking at the original function. So then what I'm going to do is I'm going to go down to the first derivative, f prime of x, and we're going to transfer these important values down. So I'm going to take that horizontal tangent, and I'm going to take that horizontal tangent. Okay, this is about a third degree, so when I go back to my derivative, it will be a fourth degree. So let's say this is 1/3 x cubed minus x. So then if I think about my graph this way, it's going to look kind of like this, and I'll explain some words about it in a minute. Notice that where I had a horizontal tangent up here, that becomes an x-intercept on the first derivative. I had a horizontal tangent on the original function, that became an x-intercept. If I did this math, my derivative would be x squared minus 1. Okay. Alrighty. Notice that I had concave down, which is a negative for the derivative. So I have a negative slope, concave up, positive slope. My point of inflection would be right in the middle. And so this is where my point of inflection is going to be. Okay, and then I'm going to go down one more. And there's lots of other things that we can notice and talk about, but for right now, we're just kind of going back and reminding you of some of these pieces of information. The second derivative is going to be 2x, and that is going to be this line, okay? Alrighty, so if I notice here, I need a different color. If I notice here, I have a negative tangent, which means that the tangent is underneath the x-axis down here. I have a positive tangent right here, which means that the tangent is above the x-axis. And then if you'll notice right here, this was my inflection point. It has now become my x-intercept. So we will spend a lot more time on this soon, but I just wanted to kind of bring back a little bit of the ideas from curve sketching. Alrighty, that's it for today. I will see you tomorrow.